Okay, can everyone see the whiteboard?
Yes.
Okay. So I don't know if I can add the image here, so I'll just put the cards in text here. Okay, so what answers did you all get for this question? Okay, I see quite a lot of threes. 3 is not right. 2 is the correct answer. Ishan or Bharat, can you explain?
Yeah, so this is Isha. So first, the cards so first we have to pick the prime numbers of that and then the vowels. So A is a vowel, so A, and then 3 and 5 are primes.
So that would give 3, right? How did you get 2?
Yeah, so I matched up A with 3, and then A with 5, and then each one of those is 1/6, and I got 1/6 plus 1/6, which is 2/6, and so it's just the numerator, which is 2.
Okay, so I think maybe one thing that wasn't clear. So these are all the same side, or these are all one side of the cards. So they're all separate cards. So I don't think you should need any probabilities here. You're just seeing one side of each of 5 or each of the 6 cards. So we just want to confirm if this statement is true or false, right? So I think the reason why you had 3 initially, and I think why most of the answers are 3, is everyone thinks we need to get A is the vowel and 3 and 5 are the prime numbers. So we have to check those 3. Now let's think about the statement a little bit carefully. We want to check, is this statement true, right? If the card has a vowel on one side, then it has a prime number on the other side. So let's think about how this could be false. So what we first are going to try flipping over the A. So if this is true, what should we see on the other side of this card?
A prime number.
Prime number, good. So if we turn over this A, we should see a prime number. If we turn over the B, do we know what we'll see? It doesn't matter, right? It just says if the card has a vowel on one side, then it has a prime number on the other side. And we know that each card has on one side a number and the other side a letter. So if it has a B on this side, it doesn't have a vowel, so it doesn't matter what's on the other side. The C doesn't matter. Now let's think about the 3, 4, and 5. We know that one side is a number and one side is a letter, right? So in the 3, what should the other side be for this statement to be false?
A consonant.
Okay, let's think about that. I think that's the, so let's say that there was G on the other side, right? There's a consonant on the other side. Is the statement now false? If a card has a vowel on one side, then it has a prime number on the other side. Is that false now if there was a G on one side and 3 on this side?
Yes, it's false.
So we have to be careful on the wording here, because it says if a card has a vowel on one side, then it has a prime number on the other side. It's not saying if it doesn't have a vowel on one side, then it cannot have a prime number on the other side, right? So if it didn't have a vowel on this side, then we don't care if it had a prime number on this side or not, right? We did the same thing for B and C. We said it doesn't matter what's on the other side, right? So if this had a G on the other side, then it didn't actually matter whether this was prime or not, right? And the other way, if it had a vowel on this side, then also it didn't matter, right? Then it already had a prime number and it's fine, right? Does that make sense? It seems like we should care about what is on the other side of this card, but it doesn't actually matter, right? Because if a card has a vowel on one side, then it has a prime number on the other side is the statement, right? So if the card had a vowel on the other side, then yes, a prime is here on this side, and that's good. If it had a consonant on this side, on the other side, then the statement doesn't even apply, because it only applies if the card has a vowel on one side, then this statement holds, right? So we really don't care about what's on the other side of 3. So which one do we actually care about what is on the other side?
4.
4. Why 4?
Because that's the only one is the even number. If it has a vowel or a consonant, will matter for that.
Good. Yeah. So this one is 4 is not a prime number, right? So if we actually have a vowel on the other side, then the statement is false, right? Let's put an E on the other side of the 4. Now the statement is false, right? If a card has a vowel on one side, which now this card does, then it has a prime number on the other side. It now doesn't have a prime number on the other side, and the statement is false. So we actually do need to check the 4 and the A, but we don't actually care about the 3 and the 5. Because if they had a vowel on the other side, the statement is true. If they had a consonant on the other side, the statement doesn't apply. Does that make sense? So in logic, if you've worked with logical expressions, this is the contrapositive of the statement that we actually have to confirm. But that is really not necessary here. If you just think about what is needed for the statement to be true, and okay, if I do turn over the 3, what would be on the other side that would make this false? That's enough to kind of figure out that we don't really care about the 3 and the 5. And all we care about is what's on the 4 here and what's on the A here. Does that make sense? Any questions on this? Okay, let's move on to the second question.
Can you explain that again?
Sure. Okay, let's, which part? Is there one part in particular?
Can you repeat why we don't really need the 3 and 5?
Sure, okay. So okay, let's look at the statement closely. If a card has a vowel on one side, then it has a prime number on the other side. So if the statement only applies if the first part is true, right? If a card has a vowel on one side, then it has a prime number on the other side, right? So let's think about, in this case, we're only seeing this side being the 3, right? So let's think about what could be on the other side. And we really care about the two cases. Let's say a vowel and a consonant. So there could be, let's say A is the vowel, or G is a consonant. Now let's think about, okay, if A were on the other side, right? So some vowel is on the other side. Is the statement true? If a card has a vowel on one side, then it has a prime number on the other side. It would work, right? It had a vowel on this side. It has a prime number on this side. The statement is true, right? So what is the case? So in that case, it would be fine. So let's think about the other possibility. Okay, there was a consonant on this side. So then if a card has, we look back at the statement, it says if a card has a vowel on one side, then it has a prime number on the other side. Does it say anything about if a card has a consonant on one side, then it does not have a prime number on the other side? There's no such statement, right? So if it had a G on the other side, it wouldn't violate the statement, right?
Yeah.
It wouldn't make it untrue if there was actually a consonant on the other side. So what this means is if I turned over this card, if there was a vowel on this side, it satisfied the statement. If there was a consonant on the other side, it didn't even apply to the statement. So in either case, I don't actually care what's on the other side of this card. If it's a vowel, it matched the statement. If there was a consonant, it just didn't apply to this case because there was no vowel on either side. So I don't really care about anything that's on the other side, but I do need the 4 because if that had a vowel on the other side, then it might actually disprove the statement. Does that make more sense?
Yes.
Okay. If
Thank
it's still, yeah, no problem. If it's still confusing, you can think about, write out the cards and then see if it had what different letters on the other side. Is the statement true or false? And I think that might help to make it clearer.
Okay.
Okay, any other questions? Okay, let's move on to the second question. Okay, I see a few answers. 3 is correct. Pavan or Preeti, can you explain?
Okay, so basically 3 of the sides were going to be green and attached to each other. So then that leaves me with 3 other sides that I could put the color. So I did 3 factorial over 2 factorial because I have 3 spaces left and then there's 2 repeating colors.
Okay, let me see. So how did you start? You put the 3 green sides next to each other?
Yeah.
They're always going to be attached to each other.
They're always going to be attached
In
to
some
each
way.
other in like some way or the other.
Okay, that is true that they would. So okay, let's look at this in this example. So one way I could do this is I could put a green side here, a green side here, and a green side here, right? Is this what you mean with 3 sides connected?
Yeah.
Okay, so if we have this, then how many ways are there for the remaining ones? So I have 1 blue side and 2 red sides, right?
Yeah.
So I could put a blue in any of the 3 remaining faces, and the other 2 would be red, right?
Yeah.
So interestingly, you can count the number of variations of that, but actually I think those are all the same. So if you think about it, let's try to draw them back. I don't know if I can make this clear. Let's say that this face is the blue one, right? This should be I can rotate this in 3 ways and get the 3 greens to still be with this corner. Imagine if I just rotate the cube such that now the blue face comes here and the 3 greens are still in the same place. Does that make sense? Okay.
Yeah.
So you could actually also, this is not the only green combination, right? This is actually different from if I had the face across from this face being green. So the one here. So there, the 3 faces won't share one corner, right? It would be this face, and the one behind it also be green. Does that make sense? So there's actually a little bit. So the final count was correct, but I think you might have miscounted 1 and overcounted 1.
Okay.
So this could also be green, right? Does that make sense? And this is different from having the 3 greens at one corner. So I think I think an easier way to count it is instead of looking at the green ones, let's start with the blue because there's only 1 of that. So let's start with the blue at the top. Now let's think about how we could place the remaining colors. So one way is blue is, so you can think about it in a cube. Once I make one of the sides blue, I can always rotate the cube such that the top is blue, right? So that at least takes out one kind of rotation that I don't have to worry about. So let's assume that the top of the cube is blue. Now let's think about how I can arrange the remaining ones. So one option is to have my 2 red faces be next to each other on the 4 sides that are next to the blue face. So this is one option. And note that this is the same as putting red in this face on this side as well as this side. So as long as those 2 are next to each other along these 4, it's all the same. I can always rotate the 2 reds such that this edge is on any of these 3 corners, right? So one option, so let's think about this. So options for rotating is, let's always have the blue on the top. Then the 2 reds are on the 4 sides, are next to each other on the 4 sides. So this is one possibility. Now another one is these 4 reds, these 2 reds, instead of being next to each other, they could be across from each other. So so this edge that's across from the red can also be red. So basically the main difference here is instead of having the two reds next to each other, now they're across from each other. So this is one option. Now, what's the last case? Where would the reds be? That's different from these two. Any ideas? What's the other face we haven't considered? We've only looked at the four sides, right? So now I could actually have the red on the side opposite the blue. So effectively the bottom if in this image. So if I put one red on the bottom, now the other red could be any of the other four sides. So this is the last case. So all the other four sides are the same. I can imagine just rotating the cube in four directions to have that the other red be in any of these four places. But I have one red across from the blue and the other on one of the sides. So this is the third method that you can do. So overall, there should be three different ways to color the cube. Does this make sense? Any questions? Okay, if this doesn't make sense, what might be useful is make a small paper cube and then try just putting a color, either coloring it or just writing a color on each side. And then you can think about how you can rotate the cube to have the same orientation. And then think about, okay, how many different cubes can you make without actually being able to rotate to match one of the ones you made already. And I think that actually having a 3D object will make it clearer to understand this. But finally, it should be these three options. And you can think about how the reds are placed when you fix the blue to one face. Any questions? Okay, let's move to the last question. Okay, good. 25 is the right answer. Sanvi, can you explain?
So the first number that is past 100 and has the same remainder for both 6 and 8 is 101 because both the remainders are 5. Mm-hmm. And so I know that the least common multiple of 6 and 8 is 24. So I checked to see if there were any numbers between each group of 24 that had the same remainders. And so for every group of 24, there's 6 different same remainders. And so I counted up. I kept on adding 24 to 101. And so I went to 101 to 125, 149, 173, and 197. And so that's a 6 plus a 6 plus a 6 plus a 6, or 24. And then you have to count 101, which is one extra one. So that's 25.
Good. Yep, that's right. So let's just talk a little bit about why it's the 6 numbers for every 24. So let's think about what this question is saying, and that n should have the same remainder when it's divided by 6 or 8. So what this means is that n can be written as 6 times some number plus a remainder r. Or n, the same number n, can be written as 8 times some number plus the same remainder r, right? So it has the same remainder when divided by 6 or 8. So what does this mean? It means that if I look at this, n is equal to 6a plus r, or n is equal to 8b plus r, this 6a and 8b need to be the same number, right? Such that the remainder is the same. So if this 6a and 8b are the same number, that means this must be a multiple of 6 and a multiple of 8. So that should mean that this number is a multiple of 24, right? It should be, if it's a multiple of both 6 and 8, then it should be a multiple of the least common multiple. So in other words, what you can say is n is equal to 24 times some number plus r, and then it should satisfy both of these, right? So then it comes down to what should be the possible values of r here. So we know that r should be, in this case, should be some number 0 through 5 to be a remainder when divided by 6. And in this case, it should be a number 0, 1, 2, 3, 4, 5, 6, or 7. So it has to satisfy both of these, right? So it actually has to be a number 0, 1, 2, 3, 4, or 5. So basically combining these, we know that it has to be a multiple of 24 plus either 0, 1, 2, 3, 4, or 5, and then it'll satisfy both of these. Because we know that it should be the same remainder added to a multiple of 6 and 8, which becomes a multiple of 24. Now this is essentially the same thing, right? We're saying in every 24 numbers, the numbers that have a remainder of 0, 1, 2, 3, 4, or 5, when divided by 24, should be counted. So that's 6 numbers for every 24. And now we can do the same counting. How many of these numbers are there between 100 and 200? So that we can see that, what's the first multiple of 24 near 100? We see it's 96. So 96 plus 4 is equal to 100, but we said between 100 and 200, not inclusive, based on this. So 96 plus 4 doesn't work. So 96 plus 5 is the first one that works. And then after that, that's 101. Now, after that, we have to go to the next multiple of 24. So that's 120. Then we can add, so 96 plus 5 is one of them. And then we have 120, plus we can add any of 0, 1, 2 up to 5. So that gives us 6. 144 plus any of 0, 1, 2 through 5. Gives us 6. So I didn't write the plus 0 to 5 for each of these, but each of these should have 6 for each of the multiples of 24. So 6 times 4 plus 1 should be 25 total. Does this make sense? So this is a good pattern to find here, that it's 6 numbers for every 24. And you can kind of confirm this by writing it out this way. So it has to be a multiple of 6, a multiple of 8. So it becomes a multiple of 24, with the remainder being any of 0, 1, 2, 3, 4, or 5. Any questions on this? Okay, then that's it for today's class. We'll see you all next week.
Thank you.
Bye.
You.
Bye.
Thank you.
Thank you.